to the de Broglie hypothesis. Yes, de Broglie's hypothesis. So initially we know that energy is equal to Planck's constant times the frequency of the wave, and energy is also equal to mass times the square of the speed of light. Yes, we have these two, 1 and 2, and we equate the two. Hf is equal to mc square. Hf is equal to mc dot c. Yes, so now P is equal to mc, as we know, as a substitution. So hf is equal to P, the momentum, which is mass times the speed of light, in this case dot the speed of light. Yes, so the momentum would be Planck's constant and into frequency by c, the speed of light. Yes, so this is what we have as a form here. And since v is equal to f lambda, so in this case c is equal to f lambda, and we put f lambda in the space of c. So here we have this equation 3, and we use the substitution b, and we get momentum is equal to hf by f lambda. So momentum is now equal to h by lambda. Lambda is the wavelength, and h is the Planck's constant, p is the linear momentum. And c, lambda is equal to h by p, and lambda is equal to h by mv. In mechanics, mass times velocity is the momentum, and in relativity it's slightly different, and we'll show you how. In relativity, okay, just we will drop relativity for now, because that's something subject to constant context, so we'll get into that later. So Heisenberg's uncertainty. Yes, so this says that the product of the differential momentum on one axis times the differential displacement on that axis is roughly equal to the Planck's constant. Yes, this is the first proposition. And the second proposition could be differential momentum on one axis is proportional to h by lambda. As we already know, this is h by lambda, we have established previously. Yes, p is h by lambda. So differential momentum about the x-axis, on the x-axis, is equal to h by lambda. And now we have two forms. So if we multiply the two equations on respective sides, what we get is, you see, what we get is delta px dot delta x uh, It's actually the division. We divide. It's by delta px is roughly equal to h by lambda. Yes, so what you see is delta x is roughly equal to now uh, h by 1 by h by lambda. H cancels out, so this becomes 1 by 1 by 1 by lambda. This basically is equal to lambda, the wavelength. And once again, if we get back to the multiplication, so if we take this as 3 and then we do what, the multiplication, which says delta x dot and see, this one was equation 1 divided by equation 2, and this one is now equation 2 times equation 3, this times this, which means delta x dot delta px is equal to h by lambda dot lambda. Lambda cancels out, so we are left with, once again, delta px delta x is roughly equal to h, which is a form, and which is rather the establishment of the Heisenberg's uncertainty principle. Yes, an important issue which was postponed, which we will now touch on, is the point charge potential. Point charge potential. And in this case, we have a charge. We have basically two charges, capital Q here and small q here, and there is a distance between these two charges, and it starts from infinity, and then there's this development, the differential development of the distances. See, r infinity, r1, r2, and so on. Okay, wait, r, yes, basically what we have here is the rn, and then we have r infinity related to n, r1, sorry, rn minus 1, and then we get here when we have basically r1, when these 2 point charges interact and close down on each other. So the electric field E is equal to k q by r square. Yes, The differential work done would be basically force into distance. Work is equal to differential work from one point, let's say n minus 1 to Rn would be initially Rn to Rn minus 1. In this case, differential work would be force, which is um, force times distance, and force in this case is so we take this approximation. Delta W is equal to force times distance minus QE times delta R, and delta W is equal to the differential work between one point Rn to the other point Rn minus 1, and so on. So this is also equals to theta is roughly equal to 0 degrees, so ft cos theta would be fd, since cos of theta is equal to 1. Yes, so we will not write that. So we will get directly to our point. Rather, in this case, theta is equal to 180 degrees, so cos theta is equal to minus 1. Okay, you see the angle on this axis is pretty much 180 degrees. So this is minus QE, and delta R is equal to, and now we put the delta R and then minus 1 from the cos of theta, QE delta R. Delta W is equal to QE delta R. And now we look for QE now, and as we know that E is equal to KQ by R square, so what we have here is Q dot KQ by R square dot delta R, and delta R is 1 minus delta R is Rn minus Rn minus 1. So this is delta R basically. It can be R2 minus R1, it can be R3 minus R2, it can be R4 minus R3 in general form. So delta W is equal to KQ by R square delta R, and delta R in this case is um, uh, uh, in this case, let's say delta R is equal to Rn minus Rn minus 1. Yes, the differential displacement from point 1 to point 2 and point 2 to point 3. So as delta R is equal to Rn minus 1 minus Rn, okay, Rn minus Rn minus 1. Yes, this is delta R, and so I will continue with, let's say, delta W from RA to R1. Yes, from RA to R1, which is KQ by R square. Is KQ by, let's say, So we have the situation where delta W is equal to KQ by R1 R2, let's say. And why so, I will just let you know. So now this is our work done from A to 1. Point A to 1 is equal to RA to 1 whole square. And then we have here R. Now we substitute this as RA minus R1. Yes. And this we know comes from R square is roughly equal to R1 R2 in mechanics, and this here in electricity, this in this case of charge, R square would be equal to R A R B, if you know what I mean. So it depends on the points where you're looking at between the differentials. So the differential work from A to 1 in this case is KQ Q KQQ and 1 by R1 minus 1 by R n, let's say. In this case, ABC can be points 1, 2, 3. And this work from, let's say, delta work from delta W from 1 to 2, let's say, could be equal to KQQ into 1 by R1 minus 1 by R2. Okay, you see, 1 by R2 minus 1 by R1. Delta W, it goes on, delta W from Rn to Rb is equal to KQQ into 1 by R B minus 1 by Rn. Yes. And let's say start off, this cancels here, and in the next term, in the first and the second, this last term cancels with the second term with the first term here, and then as we move further, then in the next terms as well, this first term will cancel with the second term here, plus minus, yes. So in the end, what we will be left with is the differential work like this. And for summation, that's about summation. So work total would be summation of I is equal to 1 up to n delta w uh, I, yes, or delta w r n to rn minus 1, the general form. So in general, and if the last point is infinity, as here has been pointed out that the last point is infinity here, small small charge can small q can be coming from a long distance infinity to the big charge capital Q. So in this case, the general form will take the form of work from infinity to be not from okay, so work from, let's say, from work from A to B would be k q into 1 by r b minus 1 by r a, yes, and then work from infinity to b would be k q into 1 by r. This is the second point here, let's say is b. We start here and call it a, for example, and we end at b. So 1 by rb minus 1 by ra. Okay, so this time it is 1 by infinity by 1 by infinity. So this is equal to k q by rb, distance from the small charge to the big charge, yes, and this is approximate. And this becomes an equation for us, or let's say this becomes a form to be used for estimations.